Hello. We're now ready to talk about the complex DFT. So up to this point we've been talking about the real DFT, and we actually could run the whole course with just that. But I want to teach you something that overall simplifies things, and which is the convention. It's going to give us a much more elegant way to describe phase, and it's also going to lend itself to a very elegant geometric interpretation of periodic signals. So now, complex doesn't mean complicated. I actually kind of hate that they're called complex numbers. I think they should be called compound numbers. They're just numbers that consist of two parts, a real part and an imaginary part. It's actually supposed to make our lives easier. We just have to introduce a slightly more abstract notion than we're used to. Okay. But before we do that, let's review the real discrete Fourier transform. You really can't see this enough times, so don't feel bad doing it again from the beginning. So a signal, so I'll say the real DFT on a signal x with n samples consists of sine and cosine components for a frequency k, which goes through k cycles over n samples. So each component is obtained via a dot product, right? So for the cosine component at frequency k, we say c sub k is equal to the sum from little n equals 0 to big N minus 1 of x at index n times cosine of 2 pi k n over n. So what this is saying is I'm going to take the dot product between my signal and a cosine, which goes through k cycles over my interval, sampled at n different locations, evenly spaced. Each sample of the cosine I'm going to multiply by the corresponding sample in my signal, and I'm going to sum up all of those products. Okay, so that's how you get the cosine component. Sine component is obtained exactly the same way, except we do a dot product with the sine instead of the cosine. So let me actually say that that's the sine now. And in the real DFT, I let k range from 0, 1, 2 up to the floor of n over 2. That should get us everything we need. Yes. So k can go up to that amount. We're normally going to deal with even numbers, so I would just say it'd actually be n over 2 plus 1 frequencies total. Okay. So that's the real DFT. Now, one of the things that's a little bit annoying about this is that I actually have to have two numbers for every frequency. Somehow I want to figure out a way to wrap those two numbers into a single number. And so I have to use something called Eulers Formula if I'm going to do this, and I have to go to complex numbers. Alright, so here's Eulers Formula. We say e to the I theta is equal to cosine of theta plus I sine theta. And so let's just do a sanity check real quick with a couple examples, and then I want to show a proof of this actually. So first, just as an example, let's imagine that we're looking at, so theta is any number. Let's say that theta is 0. Well, we better get 1, right? Because anything raised to the 0 power is 1. So in this case, I see that e to the 0, I times 0 would be cosine of 0 plus I sine 0. Well, sine of 0 is 0, cosine of 0 is 1, so that's 1. Okay, good. Sanity check. Now, if I pick another number which is not an integer, this is personally what made this difficult for me to understand at first. You know, we start understanding exponentials by thinking of them as repeated multiplication by the base. So if I was going to say e to the 10th power, then I'm supposed to have 10 factors of e. But we do eventually generalize the exponents to non-integer numbers. And so now we're generalizing them further to complex numbers. So there are other ways to define what an exponential function is as a function, and you go over these in calculus. So we're really thinking of this as a general exponential function our intuition about what it means to raise something to a power kind of goes away, but it still works out. So I just wanted to mention that. I feel like that is a point of confusion. But so we can take theta to be something else that's not an integer. So I could say, what if theta is pi over 4? Then e to the I pi over 4 is equal to cosine pi over 4 plus I sine pi over 4. Well, cosine and sine of pi over 4 are both root 2 over 2, so this would be root 2 over 2 plus I root 2 over 2. Okay, so just here's another example of an answer that you could get. All right. Whoops, I meant to say fraction of square root of 2 over 2. Okay. So you're seeing how to type LaTeX here. All right. Now, let me do a quick proof of this, which I always thought was interesting. There's an even better proof in the book, which I think gives amazing geometric intuition. It uses Taylor series, and it shows how there's a convergent series, which you keep marching along at right angles, and you kind of circle in like a spiral onto a point, which is on the unit circle. It's very beautiful. But let me just do a quick and dirty one here, which uses a differential equation. So let's assume that we have a function. So I'll say assume that we have a function f of theta equals what we're looking for, cosine of theta plus I sine theta. All right. Let's just take the derivative of this function. So if I take the derivative of this function, I go back and use my derivative rules from calculus 1. I see that this is going to be negative sine theta. And I is actually just a constant number. It has 0 in its real component, 1 in its imaginary component. So that'd be sine theta plus that constant I times the derivative of sine theta with respect to theta, which is cosine of theta. Okay, if we look at this, what we realize is that the derivative is actually equal to I times f. Okay. Oops. Because I squared is -1. That was the definition of I, right? So if I multiply this original equation by I get I cosine of theta plus I squared sine of theta. Well, that turns into I cosine theta minus sine of theta. So what we said is we have a function, if the function satisfies this, then it should be the case that the derivative of the function is equal to I times the original function. Well, something which is a derivative of itself times a constant is e to that constant times the independent variable. So therefore, f of theta, so if I now do the antiderivative of this, I get another expression for f, which is e to the I theta. So if I find that the derivative is a constant times my original function, then I can say that the antiderivative is e to that constant times theta. So there's a quick and dirty proof. Okay. Whoop-de-doo. But how can we use this to help us come up with a more concise formulation of the discrete Fourier transform? Well, if I look at this, what I see is I'm doing a dot product with a cosine component and a sine component. So what that tells me is, well, I can use, if I just accept that some of my, I'm going to have a complex number to represent just a single coefficient, but the real component of it is going to represent a cosine dot product, and the imaginary component is going to represent a sine dot product. Well, then what I can do is take this original equation, and I can say, here's the notation, x at frequency k, so we think of this as an array now. X at frequency k is equal to the sum from n equals 0 to n minus 1 of x of n times, now we're going to do, instead of sine, we're going to do e raised to the 2 pi k n over n. So I'll say e to the I 2 pi k over n. So here is the definition. Now, actually, I do want to tweak this a little bit to follow conventions. So one thing I notice is, okay, this was the definition of my discrete Fourier transform before, but you know, I was saying that if you want this to apply to general sinusoids, so a general sinusoid is written as amplitude times cosine of 2 pi ft plus a phase offset. So the convention is to define a sinusoid this way. Sometimes I'll do minus phase. I mean, that's what we did when we were in Risset, because it helped us to think about shifting things to the right. But now we're going to shift things to the left. This is actually the convention. This is why in class I got a little bit confused about the negative sign. If we do this, then the identity is, so the trig identity is cosine of x plus y is equal to cosine of x cosine of y minus sine of x sine of y. So if that's the case and we use this identity, then we can split this up here into a cosine of phi times cosine of 2 pi ft. I'm just splitting up the sum inside here. And it's actually going to be minus a sine of phi. So that was where things get a little different. Minus a sine of phi, sine of 2 pi ft. All right, so we're just remembering how do we split a general sinusoid into components. So we see that we can split any sinusoid into a cosine component and a sine component, but actually the sine component ends up having a negative sign if I add phi. Okay, so I'm going to do a little different. I'm going to do the opposite from what I did in Risset, because that's actually the convention. So actually the definition ends up being, to match this so that I'm thinking about it as coming from this kind of a sinusoid, I actually need to say e to the negative I 2 pi k n over n. Let me write this super big here, and let me make it look nice with the fraction. Okay. So really 2 pi k n over n times n. So my frequency is k over n. Actually, yeah, I guess I'll pull the 2 pi out. So I can never decide what I want to group together when I write this. But I think this is a good way to look at it. So e to the negative I 2 pi, and then this frequency k over n times n. So what this is going to do, this is going to put, so x of k will contain the cosine component and the real component, and the sine component and the imaginary component. Okay. And I guess, you know, compared to the way I wrote it up here, it would be the negative of this sign. So I really should have written this, if I'm being consistent with what's down here, I really should have actually written this as this. Okay, fine. Okay. So nice. That works. So you get a single number, which is a complex number, but it has both the real component and the imaginary. Okay, one thing we can say about this is, since the real component is the cosine part and the imaginary component is the sine part, we can actually extract amplitude and phase from each complex number here at each frequency index. So the amplitude of our sinusoid can be computed as the square root of the sum of the cosine component squared, so we'll say the real component squared, plus the imaginary component squared. So we'll say the amplitude at index k is equal to that. Just a note, you know, this has a bunch of names, and I probably will throw different names out by accident at different times, so just be aware of that. This is referred to as the complex modulus, also referred to as the magnitude of the complex number, also referred to as the absolute value of the complex number. So this comes by a bunch of different names, but we recognize in the context of this representing a sinusoid that what this means is it actually corresponds to the amplitude of that sinusoid. All right, we can also extract the phase as the inverse tangent of the ratio of the imaginary component over the real component. Okay, so cool, we can get back all the information we want about our sinusoid. A cosine of 2 pi f t plus phi. So this gets me the A, this gets me the phi. And I already knew what f was because I was probing it with the appropriate frequency, k. So let's look at a numerical example in NumPy. So let's say I have a sinusoid, its amplitude is 3, maybe it's got 100 samples, maybe its phase is 0, and let's say that, what else am I missing here? I think that's all I need to make it. Yep. Oh no, of course, frequency. We'll say frequency is 2. All right, so I'll say my signal is then amplitude times cosine of 2 pi, and so I'm going to sample it from 0 to n minus 1. That's what this MPDA range is. Divide that by n, so it should be, times k over n plus the phase. So let's see, is this something at amplitude 3 that goes through 2 cycles? Boy, I guess. Okay, so amplitude 3, 2 cycles, good. Now let's look at the Fourier transform of this. So NumPy has a method. It's in the FFT package. So it's going to do this sum here. So we say, I'll call it big X to be consistent with that. Big X is equal to np.fft.fft of little x. This is saying I want the FFT method in the FFT package. There are other methods in here like IFFT, which is inverse FFT. We'll talk a little bit more about that later. But this is going to run an algorithm called the fast Fourier transform, which takes O of n log n time. What that means is the naive definition would actually do this sum over n samples for all n frequencies actually. That would be n squared operations, but there's a faster algorithm that computers called the fast Fourier transform that takes n log n, way faster. Okay. So we got that. So let's print it out just to see what it looks like. Okay, and it's this whole mess of complex numbers. And they use J to refer to the imaginary component instead of I. That's a convention that's used in electrical engineering because I often refers to current, so just be aware of that. But it is the imaginary component. So let me actually, I'm going to plot the real components and the imaginary component next to each other. Let me plot the first 10 real components of these frequencies. And let me plot the first 10 imaginary components, and we'll see what they look like. Oops. Okay, there we go. So what I see here is, okay, this is a thing that was at frequency 2, frequency index 2, and I see that's in the cosine component, or the real component. That is the only one that really shows up. And in the imaginary components, we get a bunch of very, very tiny numbers. This is times 10 to the negative 14th. Okay, so frequency index 2, that's the only one that shows up. Just to check, see what happens if I make that frequency index 3. Okay, it moves over there. Now notice that the value of the real component in this frequency bin is actually equal to half of the amplitude times the number of samples over 2. And this is related to the fact that we looked at that the integral of cosine squared of x from 0 to 2 pi is a half, if you remember that. So that's part of why we're getting that. Okay, now what happens if we change the phase? So what if I make the phase pi over 4? Well, now we actually split the real and the imaginary right down the middle. So that's interesting. That's because the cosine of pi over 4 and the sine of pi over 4 are both root 2 over 2, right? So that was why I gave that example there. If I make this pi over 2, then actually everything's going to go into the imaginary there. So that's sort of what you see. There's one more thing I want to plot, actually, which is I don't just want to plot the real and imaginary. Actually, yeah, let me plot a few things. So I'll also plot the amplitude and the phase following these formulas. So let me plot the amplitude. So it should be the square. Actually, you know what? I can shorthand because actually numpy's absolute value will do this because it also is considered the absolute value of a complex number. That's the definition. That's the square root of the real component squared plus the imaginary component squared. So I can say do the absolute value of x from 0 to 10, and that is going to be the amplitude. I'll also do the phase, which might be a little noisy because most of these are 0. But so let me actually, I'll make the amplitude be, I'll just define that as a variable up here. I'll also say that the phase is, as I said, the arctangent of the imaginary component over the real component. So I'll start by plotting the phase down here, but I'll show you there's a problem numerically. So yeah, I can just do amp here and phase there. Okay, so the amplitude I find is 150, even though it gets split into two parts, but the phase is kind of all over the place. Let me actually just say phase times, if the amplitude has to be greater than 0.1, let's say. Actually, yes, that'll do it. Okay. All right, so the phase here is, it's supposed to be pi over 3, which, yeah, that's a little bit over 1. Let's see, pi over 4. Let's see, that looked like the same, didn't it? Hang on. Oh no, I guess I hadn't refreshed from last time. Okay, pi over 3 should be... Wow, this is really messing with me. Okay, pi over 3 should be slightly greater than 1. Okay, now we're doing pi over 4. Why is this not updating right away? Huh. This is behaving strangely. Oh, it's because I need to do the FFT right after this? Yes, before I do that. Yes, okay. Whoops, okay. That's why I was getting myself all confused. All right. Anyway, but the point is, you see that this is matching the equation that I put up here. Of course, if I put the frequency in between two bins, I'm going to get a split here. You know, I'm going to get that weird thing happening. But for integer frequencies, you see that this works pretty well. Okay, so I just want you to do a quick exercise to make sure that this all made sense.